All right, so in this video, we're going to look at some actual word problems now dealing with related rates. The first one we're going to look at is number 32 on page 160. It's titled Hauling in a Dinghy. And so take a minute, but you can pause the video and read that. It also has an accompanying picture with it, which will be a little bit helpful. So I'm going to go ahead and focus on the picture just for a second. All right, so we know it's going to be our triangle here. And generally speaking, when I work with these types of problems and I have a triangle, everything always gets labeled the same for me. The horizontal part is always X, the vertical part is always Y, the hypotenuse is always R. Okay, so in part A, we don't care about theta, so I'm not going to worry about that in this picture right now. Now, for these types of problems, I'm a really big believer in identifying what you need and what you know. If you can generally put a list of things that you need and you know together, the problem itself will take care the answer will take care of itself. So there's a couple things that we do know straight from the problem. It says it's being pulled toward a dock by a rope from the bow through a ring on the dock 6 feet above the bow. So that means in my picture that y is equal to 6. And it's important to note in this problem that is fixed. Remember, calculus is all about studying change. And so if something is fixed, we're going to take advantage of it. We're going to use it from the start. If it's changing, then we can't use it until we're done, until we've manipulated the function in order to get it to represent change. So we know that y is equal to 6. And it also says in the problem, the rope is hauled in at a rate of 2 feet per second. Well, in my picture, conveniently actually, the rope is R. That never works out for me. I just always call it R, and it happens to be rope this time. So this guy is going to be R, and that's being hauled in at 2 feet per second. And so if we're talking about the rope being hauled in, the rope is changing, right? The rope is changing with respect to time. So the change in the rope with respect to time is going to be 2, kind of. It's not going to be a positive 2. If that boat is being hauled in, the rope is getting shorter, so the change in the rope with respect to time would be that negative 2. Okay, so that's given information in the problem, but it was up to us to identify how it related in our problem, our picture with our labeling. Our y was 6, and we know it's fixed, and our dr/dt we had to extract from the wording in the problem and identify it as a negative 2. Okay, and so what do we need? Well, the problem is asking us how fast is the boat approaching the dock, and so that would be our x, right? The boat approaching the dock. So we're needing a dx dt, the change of x with respect to time, specifically when our r value, when the rope is 10 feet out. So take a minute and go back and look at the wording from the problem and look at the notation we used and compare and make sure you understand that we're just taking words that are in a normal sentence and rewriting it now using our calculus notation. Okay? So now we've got what we need and we've got what we know. In calculus, these types of problems are all generally the same in that you've got a moving situation and we want to take a snapshot of it. At the instant r is 10, what is dx dt? At the instant the length of the rope is 10, how fast is the boat moving towards the dock? Okay, and that's why, again, we want to distinguish between what is fixed and what is not. So I need to now establish a relationship between x and y and r. It's evident that x squared plus y squared equals r squared, being the Pythagorean theorem, is a nice way to start. And then I'm going to make note, y is equal to 6. That is not changing. That is fixed in this entire problem. So I'm going to let my 6 be plugged in here for y squared. So I'll have an x squared plus 36 equals r squared. Now, I know from what I need, I'll need a derivative with respect to t. I know that from what I know, I've got some information about a derivative with respect to t. So that's going to push us in the direction now of d dt'ing both sides. In doing this, on the left, we'll have a 2x times the derivative of the inside, which is a dx dt, plus a 0 for a constant equals, on the right-hand side, a 2r dr dt. Okay? So, again, what am I looking for? I need dx dt. So I'm going to solve this for dx dt. When all said and done, dx dt equals r over x times dr dt. And now I would need to evaluate. And so in order to evaluate, it's clear that I'm going to need an r, an x, and a dr dt. Well, a couple of those we already know. We know that the r we're interested in at this point, at the instant, r is 10. We also know that dr dt is going to be a minus 2 from above. And so the only other thing that we're missing here is the x. Well, to find the x, now we're ready to go back in and use this information into our original formula. Some people were probably wondering, well, you put the 6 in here, why didn't you put the 10 in there? Well, remember, the 6 is fixed. This is changing. We can only use this in the instant r is 10. Okay, so that's where we had to use take the derivative in order to allow us to find this change that we were looking for. Okay, but now we can plug it in and use it at this instant. So what I'm going to do is I'm going to take my x squared plus 36 equals r squared, and I'm going to plug the 10 in for r. So x squared plus 36 equals 100. So x squared equals 64, and x would equal 8. So that 8 that I'm using, I can plug in to my derivative. When I do this and all is said and done, I end up with a negative 2.5 feet per second. So again, in a problem like this, I'm a big believer in a picture. I'm a big believer in what you need, what you know. From there, it's finding a relationship among the variables, taking the derivative with respect to what you need and what you know, what information you have to work with, and then from there, substituting in the things that we need to be at the exact instant that we're studying a particular change. So hopefully that'll be helpful in the next few problems that you work as well. I'm going to go and clear the screen, and we're going to take a look at part B real quick. Okay, so same problem. Now it's part B, where they want us to find at what rate the angle theta is changing at this instant. And so our angle theta is going to be this guy there. Okay. Once again, I'm going to focus on what I need and what I know. The know is still going to be the same information. We still know y is 6, and that is fixed. That's a constant. We know that dr dt still equals a negative 2. But the new information we're looking at is what rate the angle is changing. So now we need d theta dt, and again, they're looking at that same time when r is equal to 10. Okay, so now, unlike the last problem, where we can't use x's, y's, and r's exclusively, right? We have to tie in that theta to this whole problem because we need a d theta dt that we're solving for. So what I want to do is I need to figure out a different relationship. And so to tie in that angle, I'm going to use a trig function. Now, generally speaking, the easiest ones would be sine, cosine, and tangent. So we want to pick one that's going to allow us to not only come up with what we need, but allow us to use the information that we know, okay? So what I'm seeing is this. I'm seeing that picking a cosine of theta to start will be the best. If I look at cosine, that's going to be the ratio of y over r. I like that because I know what y is, and I'm needing some r's to be in there. So cosine of theta gives me the best opportunity to do this. Now, much like the last problem, we're also going to be able to plug in that fixed value to start. So cosine theta equals 6 over r. Now, I'm going to take this and dt it. I know that it wants to be with respect to t because of the need and know information we have in this problem. The derivative of cosine with respect to t would be a negative sine of theta times the derivative of the inside, d theta dt. This would now equal a negative 6 over r squared dr dt. So if you needed to view that maybe a little differently, you could see that as 6r to the negative first, multiply it down, subtract 1, and then you would have the derivative of the inside, which would be your dr dt. Okay? We're, again, searching for that d theta dt, so I'm going to solve for that now. D theta dt would equal a 6 over r squared sine theta dr dt. And now we substitute. The information we know is that r equals 10, that dr dt is equal to negative 2, and then the other thing we would need would be that theta. But we can kind of beat the system a little bit here. Theta would be important to know. However, if we simply know that sine of theta is going to be equal to that x over r from our picture up here, so sine of theta would be the x over the r, and we know that the x value was 8 from the previous problem, right? The only thing that changed was we're interested in the theta. Nothing else changed, so it's perfectly reasonable to use that 8 from the previous part. And then the r value we know is 10. So sine of theta is actually equal to 4/5. So we were actually able to circumvent needing theta itself, but instead going to substitute the 4/5 in right there. So sine of theta equals 4/5. So when you plug all of that stuff in, at the end of this problem, you'll get a negative 3 over 20 radians per second. I wanted to specify the radians there because remember, calculus only works in radians, doesn't work in degrees. So our units would need to be radians per second. So again, another interesting component to this problem, the need and the know is really helpful, I found, to students. So I would strongly encourage you to consider trying that if you're having problems.